Hey everyone, my name is Rajat Lal, Product Manager for High-Speed Digital I/O. In this presentation, I wanted to show you some of the advanced features of High-Speed Digital I/O and how your customers can use them, and also show you how to implement some of these features in the High-Speed Digital I/O driver. The agenda for today is to start off with some of the fundamentals, such as voltage definitions. There's two main kinds of voltages, the single-ended voltages and of course the differential, and we'll talk about some of the differences between the two. And of course, we'll talk about timing and digital transfer, which is one of the most important features in high-speed digital communication. Then we'll jump into advanced features such as data delay and scripting, and also hardware compare and double data rate. So the first thing we'll talk about is voltage definitions. There's two main kinds of voltages, single-ended voltages and the differential voltages. As you can see, the top graph here shows a single-ended voltage, which is a one-wire system, where you have only one output value. And there's four important terms that you need to that are important here: VOL, VIL, VIH, and VOH, which is basically voltage output high, voltage output low, voltage input high, and voltage input low. Basically, when you're outputting a signal, it should be around VOL and VOH, the high and low values. And when you're inputting a signal, if the signal is above the VIH value, then it's considered a high, and if it's below a VIL value, it's considered a low. Anything in between might be considered a high or a low, and it's recommended not to stay in that region for too long. The image below shows a differential signal. Here you have a two-wire system where you have two signals being output, and basically the difference between the two signals shows you what is a high value or a low value. So for example, in this case, you have the blue signal and the red signal, and if the difference between the two is basically positive, it's considered a 1. If it's negative, it's considered a 0. And the value between the two is VDIF, which can be which is usually a very small signal around 0.275 volts. So here again, in the first scenario, you have a negative value, which gives you a value of 0, and then 1, 0, 1, so on and so forth. Some of the capabilities of the current high-speed digital devices: the 65-4X has software selectable voltages of 5.0, 3.3, 2.5, and 1.8 volts. The 65-5X is actually programmable in a resolution of 10 millivolts, all the way from -2 to 5.5 volts. And of course, the 65-6X are the differential devices that we have, which are capable of LVDS, or low voltage differential signal. The next thing we will talk about is timing and digital data transfer. Now remember, timing is extremely important in high-speed digital communication, and is probably one of the most important concerns in digital communication. This diagram shows you a sample clock, which you see on the top, and the data that is being read at the bottom. And as you can see, we are sampling on the falling edge of the data that is being read. So here it looks pretty good. The falling edge lines up with the data pretty well, and when we need a value of 56, we get that 57, 58, 59, and so on and so forth. If you violate timing, you could be reading wrong data, and which could make your entire data set useless. For example, if you increased the frequency of your clock, two falling edges might fall on the same data pattern. As you see over here, in the case of 58, we're reading the value of 58 twice, which is violating the entire data set. If you increased the frequency, as you can see here, you might skip over an entire data period. For example, here we have decreased the frequency, and we're sampling 56, and the next falling edge is actually falling on 58, and we've completely skipped the value of 57. Here's another scenario. What if we had the correct frequency, or we're sampling on the falling edge, but as you can see over here, the falling edge is falling on the transition period of data. where we do not know what we're reading at all. This is again between the VIH and VIL values that I was talking about. If you're sampling at in those regions, you do not know if you're going to read a high or a low. One solution for this particular scenario that you see on the screen here is just to sample on the rising edge. But again, as frequencies get faster, and when we're talking about hundreds of megahertz of data transfer rates, just swapping over to the rising edge might not be enough. You need some kind of mechanism to be able to change or phase shift this clock so that you can read the correct data, which is not during the transition period. And that's where we have data delay in high-speed digital devices. Data delay is basically the phase shifting of the clock with respect, or the data with respect to the clock, for both acquisition and generation. In high-speed digital devices, you can apply a value A, for example, to generation, and a value B for acquisition. So these are two independent value banks of data delay that you can apply for your device. These are typically needed, of course, for setup and hold times, transition periods of data, and also settling times. These are also important when we're talking about propagation delay, which is basically the time it takes for your delay to go from your device under test or DUT to your high-speed digital device. And if you have a 1 meter long cable, for example, it's a small value for maybe 0.8 nanoseconds, but even that, when you're talking about really fast data rates, makes a difference. So here's how data delay is applied for generation. You take the clock, and we actually phase shift the data so that, as you can see, if you're sampling on every rising edge, we're sampling at the exact middle of the data and not during a transition period like we might have been over here. For acquisition as well, we can phase shift our clock so that we can change the falling edge of my clock to be placed on the correct position of the data, and where we can read the correct data. So data delay is available only on NI65 4X, 5X, and 6X devices. The resolution for data delay is up to 1/256 of the maximum clock frequency. For example, if you're going at 100 megahertz, it would be 39 picoseconds. Here are some resolutions for data delay. Again, at 200 megahertz, it's 1/256 of that of the period, and that makes it 20 picoseconds. The minimum frequency is 25 megahertz, and at 25 megahertz, the data delay resolution is 156 picoseconds. The next feature we will talk about is hardware compare, where you can compare stimulus and response data in the onboard FPGA of the HSDIO